Hi, good morning. Today also we are continuing the proposition for point 3.4. Okay, and the third property is K of xy is a closed subspace of L of xy. Now what is meant by K of xy? The set of four compact linear map from x to y. L of xy means set of four bounded linear operator from x to y. Now here we want to prove that K of xy is a closed subspace of L of xy. Okay. Now for this what we have to prove? We have to prove every sequence in K of xy. If a sequence an in K of xy converges to some point a, then a must be in K of xy. Okay. Let an be a sequence in K of xy converging to a, capital letter A, then we have to prove that A is also belongs to K of xy. From proving this, we have to recall so many things. Okay, the first one is we have a result. An operator A from x to y is compact if and only if the image of a unit ball of x is pre-compact. What is the unit ball? D of x is, the notation is D of x. We have to prove that image of unit ball, that means a D of x is pre-compact in y. Okay, so a compact means if and only if a D of x is pre-compact in y. Now another result, if M is pre-compact if and only if for every epsilon greater than 0 there exists a finite epsilon net in M. There exists a finite epsilon net in M. Combining these two results, we get this is a D of x is pre-compact. A D of x is pre-compact if and only for every epsilon greater than 0 there exists a finite epsilon net in a D of x. Okay, that is what we are going to prove. That means to prove A is compact, we have to prove that for every epsilon greater than 0 there exists a finite epsilon net in a dx. Clear? Once again, operator compact means image of a unit ball of x is pre-compact, that means a dx is pre-compact in y. But here we have a result, M is pre-compact if and only if epsilon greater than 0 there exists a finite epsilon net in M. Okay, so a dx is pre-compact if and only for every epsilon greater than 0 there exists a finite epsilon net in a d of x. Clear? Now what do you mean by an epsilon net? A said script a subset of x is an epsilon net of a. For every x belongs to a there exists a y belongs to a such that norm of x minus y less than epsilon. Okay, so first we suppose that let a and be a sequence in K of xy converging to a, and we have to prove that a is compact. That means we have to prove that for every epsilon greater than 0 there exists a finite epsilon net in a d of x. But given that ANs are compact sets, therefore these conditions also hold. A is compact ANs are compact sets, therefore this condition also hold. That means AN of D of x is pre-compact, that means for every epsilon greater than 0 there exists a finite epsilon net in AN D of x. Okay. Okay. Suppose AN belongs to KXY be such that AN converges to A. Okay. Now what is the meaning of that? Norm of AN minus A tends to 0. Okay. Now that means given epsilon greater than 0 there exists an integer n such that norm of an minus a is less than epsilon for every n greater than or equal to n. Okay. Now here we want to prove that A belongs to KXY. For this we have to prove that a d of x is compact. That means we have to prove that for every epsilon greater than 0, there exists a finite epsilon net in a d of x. Okay. Now given that ANs are compact, therefore using the same result we get AN d of x. For every epsilon greater than 0, there exists a finite epsilon net in AN d of x. Okay. Now this you can write as for every epsilon greater than 0, there exists an integer n such that norm of an minus a less than epsilon. You can write epsilon or epsilon by 2. Okay. So as an converges to a, given epsilon greater than 0, there exists an integer n such that norm of an minus a is less than epsilon by 2. Okay. Clear? Also, for every epsilon greater than 0, there exists a finite epsilon net in M means we have ANs are compact set. Therefore, AN d of x is pre-compact. Therefore, given epsilon greater than 0, there exists a finite epsilon net in AN d of x. Okay. If you consider for epsilon greater than 0, if you consider epsilon by 2 net of AN d of x, clearly the AN d of x has a finite epsilon by 2 net. Okay. Because for every epsilon greater than 0, there exists a finite epsilon net. So if you take epsilon by 2, if you take some nu is equal to epsilon by 2, then for this nu also there exists a finite nu set. That means there exists a finite epsilon by 2 set. Okay, there exists a finite epsilon by 2 net of AN. We consider this finite epsilon by 2 net of AN as some yi varies from 1 to n. This must be finite. This so 1 by 2 etc. Yn be the finite epsilon by 2 net of AN d of x. Suppose this is finite epsilon net of AN d of x. Epsilon by 2 net of AN d of x. Okay. Now what is the meaning of that? This is a finite epsilon. That means for every, suppose if you take some any x belongs to AN, some y belongs to y or x, you can do x belongs to AN d of x. This implies there exists here some element x, you can write this as norm of x minus some, I am denoting this as some yi naught, some element in this set I am denoting less than epsilon by 2. Okay. Okay. Now for every x, but this is actually an image set. Okay, so we can denote this definition, you can write as, actually this is for any y belongs to AN of dx, there exists a yi naught belongs to set of all yi, I varies from 1 to n such that norm of y minus yi naught is less than epsilon by 2. This is our definition actually. Okay, this is by definition for any x belongs to M, there exists a y. Okay, but actually this is an image set, so you can write, you take some y. Okay, y belongs to AN of dx. Okay, for this y belongs to AN of dx. That means for this y clearly there exists an x belongs to dx. Okay, for this y there exists a x belongs to dx such that AN x is equal to y. Okay, clear? So what we get? Given AN is AN d of x is pre-compact. Therefore, given any epsilon greater than 0, clearly there exists a finite epsilon by 2 net of a and d of x. Let this finite epsilon by 2 net be, suppose I varies from 1 to n. So this is a finite epsilon by 2 net of a and x. Now we are going to prove this is finite epsilon net of a dx. For this, what we have to prove? Given any element of this set, there exists an element in this set. Given any element y belongs to this set, there exists an element in this set such that norm of y minus that element, suppose this is be some set, z must be less than epsilon. That's what we have to prove. Okay. So, given any y belongs to a dx, that means clearly there exists a x belongs to dx such that y is equal to ax. Okay, y is equal to ax. Now if you consider a and x, clearly this is a point in a and d of x. Okay, a and d of x, a and x, then clearly this is a point in a and d of x, and a and d of x is pre-compact, therefore this has an epsilon by 2 net. Okay, so you consider the element a and d of x is pre-compact, means for this a and x you can find an element in this set. Okay, a and d of x is pre-compact and this is an epsilon by 2 net of a and d of x. Okay, therefore for a and x belongs to a and d of x, clearly there exists a point in this set such that norm of a and x minus, let this point be yi naught must be less than epsilon by 2. Clear? I repeat once again. We have to prove that a dx is pre-compact. For this we have to prove that given epsilon greater than 0, there exists a finite epsilon net in a dx. We already get this is a finite epsilon by 2 net of a and dx. Here we are going to prove this is actually a finite epsilon net of a dx. That means if you take any y belongs to a dx, we have to prove that there exists some element of this set, let it be z, such that norm of this less than epsilon. That is what we have to prove. Okay, so you take some y belongs to a dx. Clearly there exists a x belongs to dx such that y equal to ax. Okay, now for this x, a and dx is clearly an element of a and x is clearly an element of a and dx. Okay, but this is a finite epsilon by 2 net of a and dx. Okay, this is finite a and dx. Therefore for this a and x, clearly there exists a member of this set such that norm of a and x minus that member is less than epsilon by 2. Clear? That member I am denoting as some yi naught. Okay. Now using same this y naught as z, what we get? Norm of y minus yi naught is equal to norm of y minus yi naught is less than or equal to norm of a minus a n x plus norm of a n x minus yi naught. Okay, and this is less than or equal to norm of a minus a n into norm of x plus norm of a n x minus yi naught. But where is x? X belongs to dx. Dx is a unit ball. That means norm of x is less than or equal to 1. Therefore, this is less than or equal to norm of a minus a n plus norm of a n x minus yi naught. Okay. But we know that an converges to a, therefore given epsilon greater than 0, the exists integer and such that this is less than epsilon by 2. We have already chosen. Okay, therefore this is less than epsilon by 2 and plus using the earlier property, this is also less than epsilon by 2 and this is equal to epsilon. This implies norm of y minus y I naught is less than epsilon. Thus we get for any y belongs to a dx, there exists a y I naught in yi, I varies from 1 to n such that this condition holds. As y is arbitrary, we get this is actually a finite epsilon net of a dx. Okay. Thus for any epsilon greater than 0, there exists a finite epsilon net of a dx. This implies a dx is pre-compact. Hope this is clear. Today we have proved the third property of proposition, and the result says that k of xy is a closed subspace of L of xy. For proving this, we have to prove that let A and be a sequence in k of xy converging to A, and we have to prove that A belongs to k of xy. That means A is compact set. A is a compact operator. Okay. For proving A is compact operator, we have proved for any open ball dx, A of d of x is pre-compact. Okay. For proving A of d of x is pre-compact, we have proved for any epsilon greater than 0, there exists a finite epsilon net in A d of x. Hope this is clear for you. Okay.